let's have half a class. So last time what we were talking about was we were talking about calculating internal loads for beams that aren't horizontal. And we started with, so back to internal loads. I'm going to call it internal loads on inclined beams. And really what you're doing is if you have a beam in like a structure that's like that, and you're doing your calculations with a coordinate system like this, the coordinate system transformation you're doing is really just to make the x-axis line up along the long axis of the beam. And so that's the, you're rotating the coordinate system some counterclockwise angle theta, and if it's clockwise, you call it a negative angle. Okay, and what you do to make this transformation is you define a rotation matrix that's equal to the cosine of that angle, sine of that angle, negative sine of that angle, cosine of that angle. And then you multiply that by your force. And I mentioned that when we get to deform, mechanics of materials, we're going to do this in 3D. We're going to have to do it in 3D. This is kind of a two-dimensionalized version of this rotation matrix, but it's a first glimpse at it. And we started with a beam well, we started with this structure. And that's a 500 Newton force. And the masses of each of these, that's supposed to be an equilateral triangle, and the masses of both of these are 30 kilograms. And so you calculate the external loads. And then once you have all the external loads, you have something like this, where you have a downward distributed load. Call this RA. Call this F12. And then there's this 500 Newton force. And you multiply all these things by the rotation matrix. So I'm going to call, so our rotation matrix in this case would be cosine of positive 30 degrees, sine of positive 30 degrees, negative sine of positive 30 degrees, cosine of positive 30 degrees. And then you just multiply. So RA, I'm going to call it RA new, like in the new coordinate system.
Oh, wouldn't that be 6 degrees? I know you did 30 in the last one.
I did 30 on the last one.
Equilateral.
It would be 60, you're right. Dang it. Well, okay, let's correct that. Thank you. Okay, so RA in the new coordinate system would be Q times RA in the old coordinate system, F12 in the new coordinate system. By the way, that under squiggle means it's a matrix. Would be Q times F12 in the old coordinate system. That 500 Newton force, I'll call it F500 in the new coordinate system, would be Q times that 500 Newton force in the old coordinate system would just be 500 0. And the force of the distributed load in the new coordinate system would be that matrix Q times the distributed load function. So notice that this Q function is the total weight, so 294.3, divided by the length, which was 1 meter. So this would just be, as a vector, 0 for x, negative 294.3 because it's down, and that would give you the distributed load. Well, let's do these calculations, calculate the external loads. Hopefully we can get to this internal loads before class ends. Okay, so first we're going to calculate those distributed loads. I mean those external loads. So first I'll do body 1. I'm going to say this is body 1, body 2, A, B, C. So you have RA, F12, 500. And now that we've chosen a body to isolate, we can represent our distributed load as a point force, which, I mean, is how we've always done it. We've just treated this like a force acting at the center of mass. And the total force is 294.3. And I'm going to use this as my about point. So first, my force RA, row vector is 0. Force is RAX, RAY. Cross product is 0. Then the weight force, the row vector is 0.25, 0.433. The weight is 0, negative 294.3. And so the cross product is negative 147.15. Then the force F12, the row vector is 0.5, 0.866. Cross product is 500, 0. And so you get a cross product of negative 433. Hold on. This is the 500 Newton force. And we still have to do the F12. So F12 has that same row vector. Force vector of F12x, F12y. Cross product is 0.5 F12y minus 0.866 F12x.
It to be the thorn in your side.
Yeah.
That gravity one looks like you did multiply it by half instead of a quarter. For mg, the cross product of mg.
Yeah. So what's half of that now? 78 point. Thank you. Oh, I wouldn't have come up with that. Negative 73 point what?
5, 6, or 5, 8.
5. Okay, thank you. Newton's second law gives us the, well, I'm just going to write these, number these out. So the x equation for Newton's second law says RAX plus F12x is equal to negative 500. The y equation says RAY plus F12y is equal to positive 294.3. And the third equation says negative 0.866 F12x plus 0.5 F12y is equal to, can you subtract those two, add those two?
506.
506.58. Okay. We have 4 variables, so we got to keep rolling. So the free body diagram of body 2. This is, it also does not make sense that that's on a roller. That is, I think when I drew it in the last class, I put it on a roller, but it wouldn't be static if that right side was on a roller. It would just collapse flat. So this has to be a pin joint. So we got RC here, 294.3 here. Force vector of negative F12 here, and we already dealt with the 500. I'll put my about point down there. So the force RC has a row vector of 0. The force is RCX, RCY. Cross product is 0. The weight force has a row vector of negative 0.25, positive 0.433. Weight force is 0, negative 294.3. And the cross product of that is, what's that?
73.58.
73.58. And then negative F12x Row vector is negative 0.5, positive 0.866. Force vector is negative F12x, negative F12y. Cross product is 0.5 F12y plus 0.866 F12x. And so equation 4 says negative F12x plus RCX is equal to 0. 5 says negative F12y plus RCY is equal to 294.3. And equation 6 says 0.866 F12x plus 0.5 F12y is equal to 73.58. Now we have 6 equations for 6 variables.
For the rotational Newton second law,
Yeah.
should that be negative 73.58?
I think it should be positive. Oh, that is a counterclockwise. What's going on here?
Like in your
Oh, I got you. Yes. Yes, yes, yes. Okay, so there's 1, 2, 3, 4, 5, 6. For the variables, I'm going to do RAX, RAY, F12X, F12Y, RCX, RCY, and then the constants. For equation 1, can you read me like the variable and then what the coefficient is? So like RAX 1, F12X 1, and then what's the constant in equation 1?
you have enough of them.
Okay, equation 2,
F1, 2, y, and RA,
that makes sense. And the constant?
294.3.
Okay. 3,
Negative 0.866 for F12x,
okay.
and 0.5 for F12y,
Positive 5, okay.
and the constant is 506.51.
All right, equation 4. Can I see it yet? Ooh, I can do it myself, just barely. F12x, we got negative 1. RCX, we got 1. No constants. Equation 5, F12y, we got negative 1. 1 for RCY, and then 294.3. And then equation 6, F12x, we have 0.866. F12y, we have 0.5. And the constant negative 73.58. Okay, can everyone solve this? And we'll make sure we don't make any mistakes punching this in. So I got RA is equal to negative 165, negative 139. Did you guys get that?
I know it's green. No.
You got that.
I got that.
That's a good sign.
No.
Wait, oh, I'm going to keep more digits than I usually do. That should be 04. And negative 138.4. And then F12 is negative 334.97. Yay. 433.
Yeah.
And then RC is negative 334.97.
Yeah.
727.3.
Nice.
Yes. Everyone else screwed up. Good job, Matt.
I don't risk.
Okay, so now here's now we're finally at something new, okay? So we have this. This is our body with its external loads on it. We have negative 165.04, negative 138.4. A downward distributed load like this. I don't know. This is my notation. So if you don't like it, make up your own notation. But this is a distributed load of, we figured that out before. So this is 294.3. I'm going to write newtons per meter just to remind you that's a distributed load. And then F12, so we have this force plus a force vector of 500, 0 at that point. I'm going to add those two. So we have negative 334.97, 433, plus a vector 500, 0. And so up at the top here, we have a total force of 165.04, 433. So we have three total forces that we need to convert to our new coordinate system. Okay, we want to go from this coordinate system to this coordinate system. Where this angle is 60 degrees. And so our rotation matrix, our angle is positive 60 degrees because it's counterclockwise. So our rotation matrix is cosine of 60, sine of 60, negative sine of 60, cosine of 60. And that is 0.5, 0.866, negative 0.866, 0.5. So our RA new is going to be that Q matrix times the vector negative 165.04, negative 138.4. Okay. And so first I'm going to multiply it by negative 165.04, negative 138.4, and I got a new force vector of negative 202.38. Is anyone else doing this?
Yep.
Are you getting those same things? Okay, good. Okay, so that is that same force vector just expressed in our new coordinate system. Okay, then I'm going to do the distributed load in the new coordinate system. So that's Q times, in the old coordinate system, this distributed load was 0, negative 294.3. And I get negative 254.87, negative 147.15. Anyone get that?
Yep.
Okay. I'm going to keep writing newtons per meter just as a reminder. And then the last one, well, the last one, if we're doing internal loads, so these actually aren't going to come up in our internal loads calculations because they're going to be at the far right end. Our cuts are never going to get there, but might as well do it. I don't know. So the right force is Q times, where is that? Negative 334.97.
Do we want to use the one off the free body diagram that has the 500?
Yes, we do. 165.04433. Yes, thank you. 165.04 was it? And then 433. And I got 457.51, 73.57. Is that what you got?
Yep.
All right. All right, so now we have the coordinate system. We have all of our loads expressed in a coordinate system rotated like this with the x-axis along the axis. So now we can just lay it flat in our mind. The only thing that matters mathematically is the relationship of the coordinate system with the body. Okay, so now what we have is this. We have a force vector over here of negative 202.38, 73.73. We have a force vector over here of 457.51, 73.57. And we have two distributed loads here. And again, this is sort of my notation. But we have, I'm going to draw it as a force going this way, a distributed load going this way of 254.87 newtons per meter. And then a distributed load going this way of 147.15. Okay, that's the complete free body diagram of this body, how many cuts are we going to need to make?
Should be one.
Just one, yep. The distributed load functions never change. There's no point forces between the endpoints. So our cut is going to go all the way from 0 to 1. And we have a force over here of negative 202.38, 73.73. Now that we've chosen a body to isolate, these are both rectangular, uniform distributed loads. And so we are going to have a horizontal force acting right down the length of the body with a magnitude of 254.87 x, because that's how uniform distributed loads work. And we're going to have a downward force of 147.15 x. And then the internal loads.
So we don't care about the centroid of the horizontal distributed force.
Right, I drew it where the centroid is, but we don't care about it because it's not going to, the only reason the location matters is for moments, and this is a force right along the long axis, so it's not going to ever produce moments, the horizontal part. Okay, so Newton's, yeah.
Still then, or no?
Yeah, that x is still going to come into Newton's second law.
Okay.
Okay, so Newton's second law says negative 202.38, positive 73.73, plus negative 254.87x, negative 147.15x, plus t negative v is equal to zeros. And so t is equal to positive 254.87 x plus 202.38. And v is equal to positive 147.15 x minus 73.73. We've never seen a tension that varies with location along the length before, you know, that depends on x explicitly, but this time it does.
I think the signs are flipped on the shear force.
Yes, thank you. Let's finish the moment thing. This, in a way, this is the important one in all this. So rotational Newton's second law. There's no moment from the stuff at the left, no moment from that horizontal distributed load. We do have a clockwise moment with a moment arm of x over 2 and a force of 147.15. Then we have plus m minus vx is equal to 0. So we have m is equal to, is this the one that's 73.58 x squared plus vx. So m is equal to 73.58 x squared minus 147.15 x squared plus 73.73 x. And so m is equal to negative 73.58 x squared plus 73.73x. All the derivative relationships we've seen before still work. There's a new one that works. Don't worry about it though, but you can imagine that there's one between dt dx and the horizontal distributed load. You can see the magnitudes anyways. The magnitude is going to be 254.87, and that's the horizontal distributed load. Okay. Okay, well, you could plot those and you'd see that everything depends on x. There is a homework problem, or there may be a couple of homework problems where you have to use that rotation matrix, but they don't include weights, so you don't have to do it for that distributed load. But this shows you that you can. Okay, so I think I'll probably assign you at least one of those where you have to try to use the rotation matrix, and then we'll go over another something like this in class on Wednesday. Okay, that's it.
I know. It's like, looks like it's ready to blast off.
Did you guys shoot up the rocket?
No.
It was nice out this past weekend though, but it was scheduled.
Hi.
Could you show me your command line?
So our
where you
launch
typed
was the
in the
last
rotation?
public launch
Just
of the year. So they couldn't like.
So there's like a rocket bus that's,
remind me
like
the things
Oh.
you typed in. when
Oh,
you
I got you.
separate The,
Yeah.
the rows and columns.
Yeah.
So anybody could
Yeah.
like launch their rocket.
Let me put it in yours and then you'll have
Okay.
it. So,
Northland?
But so like it's like a 5-mile field. They usually launch rockets, and so that's only open, certain times. So now they have a private launch like the U of M is doing that we're gonna attend. Yeah.
This is a fun game.
Turns out you can't just launch rockets whenever you feel like.
and then I usually put it into a variable. I usually put it into Q.
Airspace.
So there it is. And if I hit enter, it'll show you what that all is.
Okay.
I guess let's just hit enter and then you'll have them both. So,
I mean,
oh, okay.
the only thing is you.
So there it shows you what I entered. And that's the answer for Q.
Okay, then the store
Yeah.
command, that arrow, where was that arrow?
Store.
Okay,
Yep.
cool. Okay. Thank you.
Sure.